I just want to let this sit for a while, and I'll check it tomorrow sometime. What is tomorrow? Is it a specifically defined word that means the next sunrise, the next business day, the next rotation of the Earth on its axes? Or is it more of a temporal term that depends on context? Perhaps it's a few hours or a few thousand years. Today, it's but a bubbling brook. Tomorrow, it will be a canyon. Or in the case of a battery, 5 months. Hello everyone, Neural Hands here, and it is tomorrow, 5 months in the future. I said I would get back to this tomorrow, and here we are. So, I did give this battery a boost charge, 15 volts or so for a few hours, I don't remember, about a month ago. I don't recall what the voltage was then, but I haven't touched it since, so it's been sitting on the shelf for about a month. Let's see how this battery is doing voltage-wise. And it looks like 12.75 volts, which isn't fully charged, and I could give it a boost charge again with my power supply here like I did before, but I don't think I'm going to do that. Instead, I'm just going to go to the next step and see what the capacity of this is. Now, in past videos I've always hooked this up to some sort of load, usually an inverter, and I would just load it with that. Today I'm going to use some more scientific equipment to take a look at not only the capacity of this, but also the discharge curve. And this is what I have to test the recovered capacity of this 7.2 amp hour battery that we tried to desulfate. Remember, it was at less than 1 volt, and we recovered it with a lab style power supply in the course of only 1 day. And it is not fully charged because it's been sitting on a shelf for months, so this won't reflect the true total capacity of it. But let's at least see what it looks like in terms of capacity and a discharge curve. Now, this happens to be a Regal DL 3021. It's 150 volt, 40 amp electronic load. It is programmable, so you can do quite a bit with it. I'm not going to do a whole lot with it except to get a discharge curve on this battery. Negative is yellow. That makes sense, right? Isn't negative usually yellow? So we'll hook our battery up to this guy. Here are the discharge characteristics of this battery according to the manufacturer's data sheet. And I'm going to use this 1C curve here, which means discharging it at 7.2 amps because it is a 7.2 amp hour battery. And according to the data sheet, when this battery is new, it should discharge down to 9.5 volts at 7.2 amps in about half an hour. So I'm going to put it on my electronic load and see what it does in comparison to this data sheet. I suspect it will do far worse because we just recovered a heavily sulfated battery. Okay, I did double up the alligator clips because I didn't think these were good enough for 7.2 amps. So there's now 2 sets on here. So we'll go over here to the battery function. It's now on battery, and we will set the current to 7.2 amps. 7.2 amps. And we will put it on the apparently 40 amp range because we're over 4 amps. The stop voltage in the data sheet was 9.5, so we're going to set that to 9.5. We'll stop discharging now at 9.5 volts. And we're not going to set a stop condition on the milliamp hours or on a time. And V on is a feature we don't need, so we'll leave that alone. And we'll turn the... Actually, let's go over here first. This is where it's going to plot out our discharge graph. And this is just the time period. I'll set the full graph for 32 minutes because I'm quite sure that it will not last that long. Set a graph for voltage. Okay, we're good there. And now we will start it. And down here, I think you can read it on the screen. I'll zoom in a little bit. So down here, it's saying it's at 7.2 amps right now. The battery voltage is 10.779, and it is rising. That's a good sign. When you start discharging a battery, the voltage should rise for a period of time. You get this big droop, a recovery, and then it'll fall again. So we're going to see if that happens here, and a running total of watt hours and the time. So we'll see what that waveform looks like, but in the meantime, I want to see how much voltage loss I'm getting through these cables. We're at 11.8 volts there and 10.8 volts on here. So we do have a problem. Let's see if I can resolve that. Well, I added another set of alligator clips, but apparently I still have about 1 volt of voltage drop, so I don't want to mess up this test, so I'm just going to leave it alone. We're going to stop at 10.5 volts instead of 9.5. We can still compare it to that table from the manufacturer and get a really good idea of where we stand. So we'll go back to our datasheet table here, and instead of 9.5 volts, we're going to be stopping at 10.5 volts. Doesn't make a huge difference really. According to this, it's maybe about 30 minutes here and 25 minutes here. Now this is logarithmic, so the middle is not 30. This is probably about 25 minutes, somewhere in there. And this thing says battery test completed. Okay. And there's our graph of our battery. 9.5 minutes, which is terrible. Of course, so is my cabling. Yeah, I'm gonna see if I can fix that. But anyway, it did discharge this battery down to 10.5 volts. And instead of lasting 25 minutes, it lasted 10 minutes. Not a huge surprise. If we had discharged it slower, we would have done better. But you can see that it did recover back up to 12.1 volts and still rising. So I'm going to put this back on the charger to cycle it as we do in order to properly desulfate batteries. So I'm going to hook it back up to this charger here. Now we could look at the charging instructions on the data sheet or on this battery, but I'm going to charge this fairly quickly, mainly because I'm impatient for this video and I want to get this done. Now we pulled 10 minutes at 7 amps out of this battery, so I don't know what that is, an amp hour or so. So it's not going to take too long to charge this. So what I'm going to do is I'm going to set my current to something reasonable, we'll say 3 amps here. And my voltage I'm just going to set to 15 volts. And while that charges, for those of you interested, you can skip past this if you're not, but this is my 1000 amp hour battery bank that's all disassembled. People had a bunch of questions in my last video about how the status of these batteries is doing, and I don't use them much. I have been keeping them mostly charged. I could make a whole video about how to maintain batteries that aren't in use. It's not as simple as the manufacturers have you believe. You can't just keep them on a trickle charge. You can't just boost charge them every 6 months. None of those work when they're in a battery bank like this. It's much more complicated. But that's not the subject here. So I had these arranged in 3 sets, I guess 4 sets of 48 volts here in preparation. Well, this bottom one is mismatched batteries, but in preparation for putting them into a 48 volt battery bank for powering some inverters. This Cotec here happens to be a 48 volt one. And I have a few of these Sunny Island 6048s that I intend to try to power my whole house with. Air conditioner, oven, everything if you want. So that's a project for another day. But I took all of these batteries and I took them all out of the banks. They're completely separate, and I put them on that electronic load. I put it at a 15 amp discharge, which is the max that electronic load can support, and I discharged it down to 10.5 volts and recorded the amp hours for each of these. I did this, of course, after fully charging each of them separately with a boost charge for maybe a day to make sure they were got another desulfation cycle. These are 100 amp hour batteries. I forget exactly what the rating is at 15 amps, but it's definitely not 100. It's maybe 90 or something. Anyway, this one was 99.4 amp hours, so better than its rating when brand new. This one was 102. This one was 98. This one was 96. These were the best 4, I believe, and that's why they got paired together up on top into this one. And these were a little bit less good, and the ones at the bottom are a little bit less good. And these 2 down here were the worst of all. That's why I just paired them with these little batteries down here. So I went through quite a bit of time here cycling these. For example, this one here, you can see that the first cycle, it was only at 30 amp hours. Ouch. I charged it, desulfated it, got 47. Charged, desulfated, 44. 56. 88. 95. And I used some different methods. I did some experimentations with high voltage for short periods of time or low voltage for long periods of time. As I expected, the results were pretty unambiguous. It makes absolutely no difference. It's just how many amps you push through it. And at high rates you lose more water, low rates you lose less, so How impatient are you? Well, that's really the question. This one did recover up to basically 100%. And most of these did recover up to basically 100%. It took some time, quite a bit of, well, I don't know if it's my time. I put it on the charger and I walk away for a day. I mean, that's not a lot of my time, but you have to micromanage it. This one down here, I really spent quite a bit of time on because I really wanted to try to get all of them back. These are $500 batteries after all. So you can see the first cycle, I got 0.5 amp hours. This thing was just completely toast. Cycled, finally got up to 20 amp hours, cycled some more. Finally got up to 52, and I gave up. So I was evaporating a lot of water out of this thing by then, trying different methods, and I just wasn't successful. But it's still as good as these batteries, so I still use them that way, and it works fine. So anyway, that's my little update on this and desulfation, and I use that lab style power supply and that electronic load that I'm showing right now to do all of this work. So you can do it in fairly large battery banks with that equipment as well. Now something like this cost me, I think it was about $500. They're not cheap. This is a Regal brand, which is definitely a low end. It's probably about $1,000 for a name brand Tektronix type. You can also get very, very cheap ones that are basically just a FET and a controller on a computer heatsink off of eBay or Amazon. You can get those for under $50, and they probably work just fine. They don't generate a graph, of course. They don't have a lot of the programmable features, but that would work just fine. I got this just because. And a lab-style power supply like this, a decent one you can get for about $100. You can get super cheap ones for under $50. I wouldn't recommend that. But this is definitely something that every lab should have. And this is kind of a luxury. You don't really need it. I've always used inverters before as loads. You can use whatever you want. But I wanted a toy, so I got that. And as a note, I did drop it down to 2.5 amps, which is more reasonable for a battery this size. There's the results from our discharge test. 1.1 amp hours, 12 watt hours. About 3 amp hours was the datasheet rating, discharging down to 10.5 volts, so we're only about 1/3 the capacity, but we'll see if we can do better next time. This time, I grabbed some alligator clips that came with an inverter that I got and put those leads on here, so this will be a nice solid connection to the battery this time. So this time we will discharge it down to 9.5 volts. Over here we have the battery on the charger at 15 volts. It's been on here for about 1.5 hours, and let's be honest, I'm hungry and I have a steak waiting. That's why I'm taking it off the charger right now. I really should let it go longer, but I want to start this discharge test first. So let's see what voltage this battery can hold. And it looks like 13.5 volts and falling. So once again, this battery appears to be pretty sulfated. Let's see if we can cycle it a few times and see if the capacity increases each time we cycle it. So once again, I'll hook my electronic load up to the battery. And we will set this thing to go at 7.2 amps. We want a graph of volts and turn it on. And let's see if our voltage is more accurate this time. We have 12.25 volts there and 12.35 volts there, so we're only losing 0.1 volts. That's good enough. I mentioned in all my videos that to desulfate a battery, you give it a controlled overcharge for a long period of time, and then you cycle it, repeating that process over and over until you're satisfied. What I haven't really mentioned, and I really should have, is that if you have a flooded battery, like these Group 27 BCI batteries here, you really need to check the acid level, the water level inside the batteries. This does use up a fair amount of water out of the batteries. If you have an AGM battery like these, then you don't have to check it because you can't. But I really should mention that if you have a flooded battery, you need to make sure that the plates stay covered at all times. When it's completely dead, don't fill it full because it may overflow once it gets charged. The water level actually rises when you charge it. But they should always be covered. So add distilled water as necessary. These are all lead calcium batteries here. If you have lead antimony, they gas a lot. And the process is a little bit different just because you lose so much charge current due to outgassing. I don't think many people use those really. Most all batteries are lead calcium anymore because people don't want to mess with adding water. So manufacturers do that. These happen to be pure lead. I'm not sure what that Leoc battery is. This discharge test has been running 4.5 minutes now, and there is no recovery in this waveform, like I had mentioned. So this battery does appear to be a little bit weak, but we'll let this run until it's dead and see what the discharge curve looks like, and if we did any better than the last time. We are down to 10.5 volts, and it's dropping extremely rapidly. Really makes very little difference whether you discharge to 9.5 or 10.5, but we're going to go to 9.5 just to match the data sheet. And you can see that we did quite a bit better this time. We're at 1.6 amp hours this time. I don't know how much of that was because the battery was fully charged, and how much was because we cycled it one time. But I guess we'll find out next time, because I'm going to put it back on the charger once this is done. And the battery test is complete. There is our discharge curve. It looks like the curve is very well behaved. It doesn't appear like we have any severely bad cells. So this is actually looking pretty good, and we got we'll just say 1.8 amp hours out of it, which is 50% of the rated capacity of this battery. We started with this battery at under 1 volt. I have no idea what the condition was, but it was certainly bad. Really difficult to get the thing to charge. Now we're up to 1/2 capacity, even at a pretty heavy load for a battery this size. C1 discharge rate. So I'll put this back on the charger, and we'll try again. And there's the final results from round 2. And it's back on the charger. I have it set for 15.5 volts this time. I'll try to speed this process up a little bit at the expense of losing a little bit more water in the battery. The charge current is pretty much stabilized. If I wiggle the leads, it moves around, but has pretty well stabilized here. It was been charging for 2.5 hours. The battery is only slightly warm, so it didn't really have any problem with that charge cycle. And it's time to cycle this once more. And we have it set up exactly like before, connected to the battery with the same cables, same settings on here, and we will turn on the load. And we'll see how it does this time. The third discharge to see if we're still recovering capacity after cycling this battery. We were at 14.5 minutes, which is how long it lasted last time, and you can see that it's doing much better this cycle. The third discharge here is just about finished. The first time we cycled it, we got about 1/3 the rated capacity of this battery. The second time, about 1/2. And the third time, we got 2.62 amp hours out of it, which is almost 3/4 what this battery is rated for when new. And this started out in a junk pile, so that's not too bad. But down here, on the discharge here, you can now see something kind of interesting. This really should just roll off and fall, but it didn't. It rolled off here, and then the slope kind of changed again. So that indicates that not all the cells in this battery are balanced. Some are more sulfated or have more capacity than others. So I'm going to put this back on the charger, this time overnight, to see if I can desulfate it again. And for record keeping purposes, this is a record of our third cycle. And I think I'm just going to leave it there overnight till tomorrow, probably 24 hours later. I said I was going to wait overnight, but I'm not gonna. It's been about 3 hours, and I have time to give this another cycle, so I'm going to do that before the end of the night. So I'll shut off my charger. Battery is hardly warm at all. Turn on my electronic load, and hook up the battery. Put it on battery mode, and set it back up. And there we go. It is running. So we'll see how the battery does on this cycle, the 4th cycle of desulfation. And the discharge cycle is complete. So this time we got 3.2 amp hours out of this, which is really, really good. 3.5 is about what this battery is rated for when brand new. So given that this battery was pulled out of a salvage lot, we were able to recover it to very nearly 100%. I'm going to put this back on the charger overnight once again, but we've been very successful in recovering this battery. Now this discharge curve here looks pretty normal. This time I didn't start the graph until I started discharging it. That's why there's not that big drop in front. So this time it started here, but it looks very normal until here, and then right here about there's an inflection point where it should continue falling, but instead it starts recovering. So there's at least one cell in this battery that still needs some work. And I'm hoping that when I leave this overnight, we can improve that particular cell. Some of you at this point may wonder, why would you spend that much time on a battery that costs $25 or $30? Well, I don't know. I mean, it's your choice if you want to, but the point here isn't to recover this battery, it's the exercise. You can use this process on any battery. You can use it on a 200 amp hour battery. You can use it on a battery that costs $1,000. It's the same process. I used this exact equipment, this electronic load, and this charger on $5,000 worth of batteries that I own, and it worked just fine. This is just a demonstration on this battery. It's small and easy to demonstrate on, so that's what I'm using. And again, for record keeping purposes, this is what we got. 3.2 amp hours, 26, almost 27 minutes. I recharged this battery fully a few days ago, and we're going to start the next cycle here of desulfation. We can see something encouraging on this graph. The portion where I started the discharge is not included on this graph. It is included in the numbers down here. But in any case, after the voltage fell, it started recovering and then started falling again. This is what you would expect out of a good battery. Well, that's not exactly what I expected. We only got 2.5 amp hours this time out of this battery. I am not exactly sure what is going on here, but I do have a theory. I have two theories why this battery performed worse last time than this time. Number one, it might have a cell that self-discharges. It has a failure in that cell, and it discharges over time, so that one weak cell causes this to fail early in a self-discharge test if I let it sit for a few days before I use it. The second option is that I'm discharging this at a really high rate for a battery of this size. It's a C1 rate. This time I recharged it very quickly so that this battery is quite hot. It's only been an hour and a half or so of recharge, but this is at maybe 120 Fahrenheit, so quite warm for this battery. And I'm going to disconnect it from the charger and immediately try discharging it. Now, a higher battery temperature is going to cause it to have a lower internal resistance, and that will make for a better result on the discharge test. I could do this at a lower rate and determine if it's the internal resistance or not, but for now I am just going to do this and see if we can get a better result this time. When I got that 3.2 amp hours, the battery was quite warm because it was a quick cycle, so we're going to try this again and see if we can repeat that. So I recharged this battery at a very high rate in order to make it hot, and it is still quite warm. And we can see that it got about 3.9 amp hours out of this battery this time, which is better than what the battery is rated for when it is brand new, and significantly better than the 2.5 amp hours I got out of it last time, when it was room temperature and had been sitting for a few days. Now, is this because the battery has a bad cell in it that has a high self-discharge rate, and when I let it sit it discharges and disrupts the battery? Or is it simply because the battery has a high internal resistance, and when I make the battery hot by overcharging it or putting it in hot water or anything else, its internal resistance decreases? Well, I don't really know, and I don't think I'm going to find out in this video because this has gone on long enough, and the point here isn't really to determine exactly how to restore this particular battery here. It's just the idea of restoring batteries. Now, I could take this battery, recharge it, and discharge it at a very low load, say 0.1 C or 100 milliamps or something, and see how many amp hours it has. If I do that, the internal resistance will play a very small factor, and I can get a really good idea of the capacity of this battery. It won't tell me the internal resistance or the useful capacity at a high rate, but it will tell me the capacity of it. I could, on the other hand, recharge it and quick do a discharge on it to see how many amp hours it has, and then recharge it, let it sit on a shelf for a week, and redo the discharge. And if this is a more valuable battery, that exercise might be valuable, but I'm just going to stop here. This shows that there are potential problems with desulfating batteries. That's always the case. You will never get a battery back up to 100% capacity. This one we showed that it's pretty darn close in some aspects, but it's never going to be new. So this is absolutely a useful battery at this point. It's not perfect, probably never will be, but it is recovered, it is desulfated, and it is useful. So, this is NeuroLarsHands, and thanks for watching.